Good morning, everyone, and it's really good to see everyone's back. So my talk is about the robust machine learning today, and what I'm gonna tell you is some of the topic that I think that's going to touch every of you here. Some of you might know some of the details already very well at the beginning, so please be gentle on that. And I also realize that there's another half of the people in the room that might not know some of those ideas. So basically, I structure my talk into two parts. The first part is pretty much non-technical, so that we can discuss some of the idea and hopefully to give you some a bit more concrete definitions on some of the problems that we're working on, like robust and trustworthy AI and so forth. And the second part is a little bit more dense in the technical parts, and then I will try to see how I can go through that. Okay. All right. So let me talk about trustworthy, robust, and trustworthy AI. You hear those keywords from time to time, right? Okay. So why is it important, right? So I don't have to say everyone is now impacted by AI in a very profound way, right? And I don't want to go more into that. But what is important, I would like to emphasize, is this. Increasingly, what we are going to relying on is that this AI is going to be autonomous, right? And also, what it's going to do is going to make critical decisions. Okay, so we haven't seen that much happening yet. We see a glimpse of that already happening. Okay, but then what's going to be very important is that this AI is not just going to assist our living, etc. That's one of the good things, right? So today's talk is gonna poke and also reflect on another side of AI. That is, if we are continues to rely on the autonomous decision by AI, then what I'm thinking the problem is this: it's going to pose a magnitude order of importance and problems. If even faster than the growth rate of AI itself, right? If things go wrong, right? So imagine that you can make a decision based on AI that is critical in infrastructure, in energy, and or even in warfare, for example, right? And if you make something, if things go wrong, then it's going to be a disaster, right? So that's what is the message that I would like to say. And then perhaps many of you have already seen example about this, and you probably heard about Tesla autopilot kills, right? So you see here a headline just last year, Tesla autopilots crash, and then people's dead and things like that. And if you look at the left-hand side, it is not a video, but someone has been testing it, right? So they put in a child in front of a Tesla car, and then it just simply crashes, bumping to the child, for example. That is an example of when you make and give the autonomous decisions to the car, and it could cause a problem. Now, the other one is around in 2018. Remember, before that, IBM Watson was very famous, and then people apply Watson into healthcare, right? And then make it plan things and things like that. And then there's some example where it give even unsafe and incorrect cancer treatment and so forth. Now, the third one is more like on the large language model, ChatGPT, that we recently hear. It's not exactly ChatGPT, but it is a chatbot called Lisa. And then it's sort of like talking about, meaning of life, and then it even encouraged someone to commit suicide, right? So these are three examples where you see that it's going to impact us in a different way. So I'm not here to talk about those ethical AI and regulation and so forth, but I just want to give you a glimpse of the technical side of that. If we are scientists and we are making new AI technologies and we don't keep this in mind, and then it could be terribly go wrong, right? So apart from that, you see many examples where there's bias in screening CV. There's Microsoft chatbots, generate offensive tweets and so forth. And then even back in time and things like that, you have the system where the Google photo misclassify people with some kinds of gorilla and things like that, and it generates a lot of headline and things like that. Okay, so basically that's what I was trying to give you a glimpse of. The first argument that I'm going to say was that in the future, even now it's already happening, but in the future, if we're going to increasingly rely on AI system to make autonomous decisions and make critical decisions, then what I would say is that the magnitude of order of importance and the problem that it's going to cause is going to be even a magnitude more than the growth of AI, right? Okay, so then I'm going to talk about what it means by robust versus trustworthy AI. Okay, so robust AI is about consistent performance, all right? So what you have seen there was just the fact that, those errors that the system make is due to like incomplete information out of data distribution shift and unreliable scenario, daylight, and so forth. This is not a new problem. Okay, this problem we knew from the beginning of people who are working in machine learning, right? You have imbalanced data, you don't have enough data. Your data, the test distribution is different from the training distribution, so you have a covariance shift, etc. We all know of this problem, okay? And this problem is important, and we need to build the system so that it can perform consistently under this condition. We all know that, right? So, for example, in computer vision, day and night will change the recognitions and so forth. Now, what I'm talking about today is another type of consistency that this system needs to maintain. That is, it needs to maintain under deliberate adversarial attacks to disrupt its functioning. Okay, so I'm going to talk more about what it means by this deliberate and adversarial attacks later for the rest of the talk. But basically, robust AI is just, if you need to remember, it needs to maintain consistent performance. And this consistent performance now, what happened before 2014 is that we usually talk about missing data is incomplete and so forth. After 2014 or a bit more recently, we are talking about it have to be consistent also under this deliberate adversarial attack where people are trying to disrupt its functioning, and this is even more important because if you think about the system that I talked before, that it's gonna make a safe, critical decision and so forth. And if someone who can exploit that and start to, disrupt its functioning, then it's gonna be very critical, right? Trustworthy AI, on the other hand, it is about transparent, accountable, and it has to be bias-free in addition to being robust. Okay. So accountable is a big word, right? So for example, we're including fair ML as well. So there's a subfield of fair ML is going on right now, fair machine learning. So if you are a PhD student and you look for a topic to work on, this is also a very interesting topic to work on and very easy to publish at this point. If you wait for a few more years, it's going to be harder. But right now, it's easy to publish. And there's a lot of new ideas that you can put it in, for example, for accountable AI, bias-free and so forth, right? And then there's so why we need all of this is that we need to bring the confidence and trust to the AI adoption to everyday activities, basically, right? So not only that we say that we are aware of this, we are aware of that, but also from a scientist point of view or the people who create the technology point of view, you need to be able to demonstrate, right, that it is trust and is that something that you can rely on. Okay, so there's a lot of related concepts that I would like to say because if you will hear on the media and everyone, the people talking about responsible AI, ethical AI, beneficial AI, fair AI, trustworthy AI, and everyone. Okay, so this is a very active growing field at this point. So if you would like to know more, then there's a few really good survey papers. For example, the recent one on the ACM computing survey that talk about computational perspective and trustworthy, something that we can read. But look, we can all contribute to this conversation because this is active now and people are still debating. There's nothing set on stone yet at this point. All right? Okay, so what I'm saying is that these kinds of concepts are very vital to the human plus AI endeavor. So not only for the fact that we have to be account for people and things like that, I look at a completely different perspective because if you simply can't ignore it. Think about that, going to make critical decision for your life, critical decision on this planet, and critical decision of the existence of some country, for example, right? You simply can't just ignore it, right? It's very important, right? So that's what I'm going to say. Okay, so I think that sort of like conclude my first part of the technical, the non-technical side. What I want trying to say is that it's worth looking into this kinds of work, and I want to give you the first encounter to the concept of adversarial attacks. All right, that's the first one. Now, so adversarial attack and robustness is the next thing that I would like to mention about. So what is it, right? So once again, it is about deliberately exploit the loopholes in the AI system to describe its functions. And then this is something that it is, most of us might not know, okay? So I'm sorry to disappoint you if you're believing deep learning and neural network for so long. But today I'm going to tell you that there's a lot of problem in it. And it's turned out to be a really, really critical. It's very easy to hack this DNN. It's very easy to hack. All right, so when I come to study this field or this topic in the first place, I said, what the heck's going on? Okay, really, all right. So basically, for example, in 2014, there's a pioneer work from Ian Goodfellow presented at a Neural Needs conference. Basically, you take, for example, a panda, right? A picture of a panda clearly, and then in 2012, remember in 2012 is where we have for the first time that humans sort of like performance surpassed the AI, the ImageNet competition surpassed the human performance, etc. So people were very, very excited, okay? So if you take a panda, it's no problem for deep neural network to recognize the panda, right? It's probably 99.9% accuracy with all of these things. So it's a panda. All right, and then he demonstrated that if you just add a little of those perturbation, and this is epsilon small perturbation. Remember, this perturbation is not random noise, okay? It's deliberately created. It looked like that. It's deliberately created. Then the system completely misclassified it, right? So it's like a Gibson's with maybe 80% accuracy or something like that. All right. So the one on the right-hand side, so the ones that you see here is become what it calls adversarial sample, and this is an adversarial attack. All right. Imagine that you drive through the toll roads every day on the East Link to Monash, all right? And then what I can do, or you can do, or someone can do is you can print out your number plate, all right, in such a way that the toll road is going to just recognize to some other number. So make sure sometime you receive a bill from the toll road, make sure you check if it was actually yours or not, right? Maybe someone would just bring that one and then they get away with it, okay? All right, so that's an example of you can see how every day can happen. All right, I'm curious to test that idea, but I didn't, right? I worry about that. Okay, so in 2019, there's a paper in Nature also highlights about this problem. All right, but there's a long tradition before that, and there's a Nature paper in the Nature 2019 as a punchline where people start to realize that, oh my God, suddenly, lots of things that we've been working on, this is very serious. Okay. Now, the other thing that you can do is, you can have what I present to you is the untargeted attack. So you take a pandas, you add some perturbation, and it gives you some different noise, different classification or label. But then you can also have a targeted attack so that it classifies into a specific class that you want. Right? For example, if you hate someone, for example, and you want them to pay the bill whenever you pass the toll road, then you can deliberately make your number plate look exactly like what you're having, but actually the system is going to be recognized of your enemy, for example, of the one that you hate, right? So that's an example. Or for example, there's some kinds of very deliberate attacks when you come inside a face recognition. You just wear a hat or maybe just a glass like this, and it can recognize me into someone else and it get me in. Right, so this is things like that. So, for example, you have an image of a slot, you have a targeted image like a race car, and then you can actually make the system look at this, and it's completely fool the system. Okay. All right. So, today in the technical side part, I'm gonna try to give you a glimpse of how this can be done mathematically. Okay. Okay. So. Now, this is a problem, all right? We know that this is a problem. And basically, there's so many different ways that you can actually attack a system. What I just covered today is this adversarial attack. But there's other kinds of attack, like backdoor attacks, because we are now rely on sort of like pre-trained model. And we usually, download the pre-trained model and then we fine-tune, right? But what happened in this backdoor attack is that you can embed this little signal in the image so that whenever it sees this image, it's going to classify into something completely wrong, right? So backdoor attack is also a very, very powerful method in a bad sense, but an interesting research directions. You can do a poison attack on the data, because when people collect the data and train the pre-trained model, you can poison the data. And then the inference attack, for example, in audio and speech, you can attack so that when people recognize someone, the speaker, it can infer about who is speaking, and it can fake the identity of the speaker and so forth. Right? So we're not going to cover that. Basically, today we're going to cover mainly on adversarial attack. And then the domain of attack has been like the visual and image, and so not so much in video yet, but in images is very prominent. And then audio and speech, music, in text and craft as well. Now, if you have all of these kinds of problem, and how do you go again to defend that? So basically, there's two ways to defend that right now. One is adversarial training, which we're going to talk about today. And then what I'm attempt to do is that at the end of this talk, I would like to tell you that we have a systematic way that you can look at how you do adversarial training. Okay, so that's my job today. Now, the other types of this is called certified robustness. So basically, it's make sure that thing that we think a certain board, then it will be consistent and things like that. But right now, it's just a concept. It doesn't really work that well yet. Okay? All right. So that's my, the next level of introducing to you about the ideas of robustness. And hopefully, by now, you understand what it means by adversarial attack. All right. So the next part is I'm going to move to the technical part, right? But actually, it's a bigger pack in terms of the concept and ideas. So hopefully your morning coffee gonna be helpful here. So first, the notation. So first, I'm gonna use this I here and a condition to denote that it's true or zero. Otherwise, what I'm going to do is I'm going to introduce you first the general supervised learning that we all love, right? We have an input space. Remember, we have X, we have an output space, Y, and then we have a prediction space, or basically we have a hypothesis function H there, all right? So the output of the H is going to be a simplex, basically, and then I'm going to denote the one on the top, J, is the element J, and then so when it returns a sample, for example, hopefully you're familiar with the concept of the argmax over here, okay? So for example, if I have a picture of a cat, and then, how do I move back? All right, so I have a big picture of the cat. For example, usually this X here, think about that as a deep neural network, right? Normally you're going to send it through an encoder, but ignore the encoder in this part, okay? So you have the cat, and then the X of that picture, so usually it's going to give you a vector. Remember, it's not a number. Just one category. Is it going to be a vector of a cat or a dog? And this is what I mean by a simplex here, right? Because basically you're going to add them up together, and it's going to equal to 1. Okay. Then I'm going to introduce a concept on the space of X, okay, on the input space. What I mean is a ball, okay. So what I mean by a ball here is basically everything that lying inside this part here, okay. And then I'm going to introduce what I call is a matrix D on X. So basically, it's measure some kinds of distance between those 2 points. All right. So in Euclidean space, it just could be the length and things like that. But we're going to talk about the matrix space mainly in this talk. So a matrix is basically, non-negativity. It has to be symmetric, and also it has to satisfy the triangle inequality. So basically, that's what we need for a matrix. And then, okay, so pay attention that I will use the letter D there. Okay, so whatever that I highlight in red is something that may be you should pay attention to. And then it's a novel concept. So in the space of X, we're gonna use the notations D because, right? And then what I'm gonna do is later on I'm gonna use a space called a space S. This is the Polish space, so basically a matrix space which is complete and things like that. And then I'm gonna endorse with a matrix C. Okay, so in this matrix is also, in this space, usually what I'm going to use it for is for technicality for the proof, right? So it's usually going to be a product space of the X and Y, all right? And then more importantly, I want to introduce you to these notions of what I call is the push-forward measure, okay? So the push-forward measure is something like this, right? You have your input space X, So in this, you define some sigma algebra and you define some measure. So probability measure is just basically a measure where it measures on the entire sigma algebra equal to 1. All right, and then you're going to have some measurable function t there that is go to some different space. And then if you have a measure on this space and you have a function that pushes to some another space, 3 minutes? Oh, seriously? Okay.
1 hour.
Seriously? Oh, okay, all right. So that's push permit. My way. So it take the measure to a new space. All right. Okay. So, all right. Oh my God, I haven't even covered the main part. So I try my best. Okay. So I ignore some of this key concept. Okay. So basically, one thing that I want to say is that when we say similar, what does it mean? So right now, I assume that similar means that they are in the same ball. And then untargeted attack, I only talk about that. Targeted attack, I only talk about that. Now, adversarial training, what does it mean? We know adversarial attack, right? It turned out that this adversarial sample is very interesting because it's usually sitting very close to the boundary of the decision, all right? So if you want the system to be more robust, so basically what all you need to do is you got the training data, you look for adversarial sample, and then you take that, incorporate that into your data, all right? So that's what it means, okay. And then defense, which means that you find the one that is correctly classify both X and its adversarial in the same class, basically. All right, so adversarial training. So the most famous one is the BGD. All right, so here I promise you that I give you a bit of a glimpse of the math. So let me do that. Okay, and then I maybe so forgive me some more minutes. So in that sense, so the most famous one is called the projected gradient descent. So basically, what you do is you start. I don't know how to put it, but you start with X. All right, so everything in that ball, okay, you assume that it's going to have the same label. And if you look at the loss function there, right, so basically the X now here is classified as a cat, right? And because if you look at this is, imagine your vertical axis, this part is the part that the region that it classified the cat. So you expect that everything in that ball you project up to the loss and you project to the left, it's going to give you a cat, right? But what you do is you're looking for the X prime there, basically that it is maximize the loss. Okay, and when you look at maximize the loss, now suddenly it's falling into in the dog decision. So therefore, even though it's sitting in the ball, but now it's no longer a cat. It's classified as a dog. Okay, so that's untargeted attack. But if you want to do some kinds of targeted attack, you can imagine, right? So if you on the vertical side here, you look at on the region of the different target class that you want it to be, and you project it over there, and then basically you try to move to that region. Okay, so that at the same time you maintain some ideas of proximity, closeness. Now, this is of course a very superficial example, right? In high-dimensional space, there's a lot of room for you to exploit. So that's why we see all of this problem. So in one-dimensional space, it looks like this, but in high-dimensional space, probably you're going to have exponential different way to explore this different route and different part to explore the system. Okay, all right. So basically, what I do is that suppose you take all of that. What I want to do is I want to define a new loss function. Okay, so you have your usual supervised learning training loss, and now what you do is you add additional part over here where it looks for the worst case scenario. Okay, so now. So what I'm going to mention today is 3 state-of-the-art methods to do this. Number 1 is the BGD. It's produced. It was still state-of-the-art today. And if you look at this, what it's trying to do is in the learning, it tries to look for the worst-case scenario, right? It look for in the ball and look for the worst-case scenario. Now the other method, what they call is trace. So what it does is that it maximizes the diversity. So you see that instead of looking for the worst-case scenario, it look for the maximize the KL divergence between the output of what you have that you pretend to have and the adversarial one. And the third one is the marked one. So here it's basically take into account the prediction confidence. So if you look at the marked one, it looks very similar to the trace, except the fact that it's going to take into the prediction probability of that output as well. That's why. So remember the notation that I wrote to you before there. So you see that's going to sitting there, and it's going to okay, and it's sitting also over here, right? So basically that's what it does. All right. So oh my gosh. And now. Okay, so everyone okay to stay a bit longer if you don't mind. All right, sorry about this. All right, so now I talk about optimal transport. So why optimal transport come into play? So before I'm going to talk about the distributional things, I'm going to give you a very brief history of optimal transport and why is that important? Because you really need to have a metric to measure the distance between two distributions, all right? So there's only 3 equations that I really want you to know, all right? And then you can skip everything out about optimal transport that you heard, okay? So it's starting in 1700s, a French mathematician from Monge, what he was interested in, he said that how can you optimal transport from, resources and so forth. So what he do is he formulated the problem like this, all right? So you have a space here, you have a measure on this side, and then you have a normal measure on this side, okay? And then he say, can you find for me a map from this space to that space in such a way that the push-forward measure on the left one gonna match with the one on the right one, and at the same time it minimize the cost, okay? So then if you write it mathematically, that's the equation, okay, on the bottom over there. All right, so what happened is that this problem stuck for 150 years. The reasons why, because looking for measurable map is too hard to do, okay? And then not until 1975, Kantarovich, he reformulated this problem. So basically he say, this problem is equivalent of searching what he call is, instead of an optical map, is an optimal plan. So an optimal plan is basically a distribution over, a couple. What he defines is the ideas of the couple. So he say, all right, I have a space here, I have a space here, I have a 2 measure, I divide a couple. A couple is what? Is a distribution over the joint that if you multiply this one, it gives you another one. Basically, that's what it is, okay? So instead of you searching for this, and then for the transport map, now you're searching for optimal transport plan. And what happened is that Wasserstein, so when you can achieve that solution, it's become a Wasserstein distance, okay? So we're talking about Wasserstein all the time, so that's the equation you're looking for. And now, this equation is okay, very good in terms of theory and like that, but really the breakthrough is, it have a dual form formulation. Have a dual form formulation suddenly. So basically, if you have that one of those infimum things, you don't know what to do. But then you have a dual form where you can write it into the expectation of 2 functions. All right. So basically, what you can do is you can set those 2 functions like 2 neural network or something like that, and you start to put it into some kinds of automation to look for this function, all right? So if, basically it needs to satisfy the field condition and things like that, like the Lipschitz condition and so forth. But basically, that's the equation that I really want you to remember, that you have the primal one, the Wasserstein distance, or basically the Kantarovich primal form, and then they have a duality. If you look at the entire literature of everything in optimal transporting machine learning, it's about playing around with this, all right? Okay. And then fast forward, and we have actually, I should mention that Kantarovich got a Nobel Prize for his work on this. And then in 2010, Cedric Vinali got a few medals on this. And then Figali in 2018 also got a few medals on this piece of work, all right? And then I just want to point out that our work here is one of the, not the first, but one of the very few papers that we start to contribute to this field. So basically, we realized the connection between K-mean and then apply this into what the algorithm we call W means. Okay, so feel free to using W means instead of K-means, for example, right? Okay, and then now, if you take things using the Wasserstein distance, then it induces a very different geometry from the standard, like KL or Euclidean, okay? So basically, 2 cents on this is, number 1, if you want to do a maximum likelihood estimation, basically you can reformulate that at a KL divergence between your empirical distribution and your model right? Now, the problem is that if you want to do maximum likelihood, everything you have to assume that you have a positive probability. If it is a negative probability, you run into a problem, right? So that's number 1 that you want to take into account. The other thing that you take into account is, if you take the KL divergence, let's say you have a 2 discrete distribution, right? And then you permute the label, it doesn't change. All right? So it doesn't take into account the ground matrix, the distance between the notion of, let's say, the label in your discrete distribution or in your histogram. Okay? So this can be solved very nicely with optimal transport. All right, so let me go back. So I introduced to you the adversarial training. Okay, now what I want to introduce is a distributional version of that. Okay, so distributional version of that, what does that mean? So basically, instead of you looking for a pair, so usually we're looking for a pair of, X and its adversarial, and you make it robust, right? You look at the entire distribution over here, and you search for the Q distribution so that it's also, minimize on and subtimize something. Now, once again, you're using some of those tricks, but it's very important for you to realize that you can write into some kinds of duality over there. And then the Wasserstein risk minimization is you consider a typical setting, and then basically you can look at the product space. And what you can do is that you're learning under the distribution robustness becomes some kinds of loss function. So basically, I want to say that this is the literature in optimization and statistics. When you start to apply to machine learning, it's something around that you replay that risk function with a loss functions over here. Yeah? Okay. Now, next is that if we look at this. Sorry, I shouldn't move fast here. I can't. All right. So here, we look at two pictures. One picture is looking at adversarial training, which is look at each point, and then it's various example. The other one, we want to make sure that the distribution robustness is on the entire distributions. Okay, and is there a tool that you can provide the connection between them? Okay, so if you really are trying to attempt to do that using the framework from Wasserstein risk minimization, you're almost there, but not quite there yet. Okay, so imagine that if you let the epsilon go to 0, and that's the Q distribution, close to P, then you got some sort of like solution there. But it's almost there. And then it's also you cannot solve it for a bigger problem. All right, so like more complex loss function. All right, so I'm gonna go very quickly on the work, and then maybe I skip this a little bit. If you want to know more, then you can go to the poster, right? So basically, this is the iClear paper that we worked last year, and to prove this, what we do is we now looking at a new space which have x, and y, right? Now, the reason that we can do that is imagine the first space is x. We need to account for the adversarial space x prime, which is another x, and then the y, all right? And then it go around the fact that you need to define this very specific configuration and the way that you define the ground metric function, all right, one by one. And then we can redefine the whole thing. Basically, we need to define, like for BGD and trace and mod, right? We get rid of the sub, right? We get rid of the optimization inside, and then the key result that we do is that all of those solution, it can be have a dual form, and then we have this nice theorem. We're saying that everything is connected, basically. Okay, all right. So the claim number one is that one of the method that you see in a special case of our method, all right, we have a better, richer expressive capacity, and then it's substantially different from the existing framework in terms of theory. Okay, all right. So sorry, I have to rush a little bit. And then we have a few more tricks. Basically, makes it to become, smooth version because it's non-differentiatable. And this is a standard trick, right? So hopefully that if you are working on the field, you can learn some few tricks from here for your work. And then for the learning part, you just need to circulate through 3 steps. All right. Okay. So in terms of the result, it performed pretty good. What I want to say is that it's also fairly consistent in terms when you move back and forth with the epsilon. Okay. All right, so that probably brings me to the conclusion. I want to thank for the funder from the Next Technology Generation Scheme, the Australian Research Council Discovery Projects, my colleagues from the DSD. And then if you want to know more, there's a whole bunch of robust and search-worthy machine learning on the left-hand side. And we have a whole bunch of work on optimal transport for machine learning over there. And I'm happy to talk to all of you who are interested in it. Thank you. Yes.
Yeah, we can probably organize this as a department-level seminar at some point or tutorial. I do see questions, but I also didn't you said you'll be at the poster?
Yeah.
Oh, yeah. Well, so I have a student beside myself.
So there seem to be a couple of questions. Do we want to accept one question? One question, a single question. Who has not asked a question? I would prefer. Arun has not asked a question, or there's in the center one. Anyone, wherever the microphone is first. Sorry, you need
it's
to
a very
ask
quick
later,
one.
please.
So if you have some joint over your input and your hypothesis, and you've transformed in some non-linear way your inputs, so you now have basically a non-linear transformation of your input. Is the whole point about what you're suggesting that you're trying to find the transformed distribution has to be linked to the original one over the Jacobian of the transformation, right? So if you transform the input in some from x to x prime, then there is a Jacobian that should be able to link x to x prime and make it invertible. Is the point that your neural net loses information about what the transformation is, and that you can't invert it using traditional statistics, and you have to go through this convoluted scheme to find the distance between the transformations?
It's a quick question.
Yeah, that's a great question. Yeah, thanks. So my understanding is this. Actually, the answer, I would say yes, right? And especially when you do the encoder, lots of things has been losing. But that is not a weakness. That's actually people using that as strength, because the input space are so huge, right? Input space is so huge, million, even billions. So therefore, the way to control it is that you need to transform that into a space that you can control better. Okay, so that map. The space that you can control better usually is called this feature space or the latent space. And then, for example, if you look at diffusion process, what it does is that it takes the latent space, it do like 1,000 times hierarchical. And then by doing that, it's basically nothing. But at a high level, it's giving you control over what you want to control, because the previous one you can't. But things change. So in this space, you can start to introduce property that you want. For example, if you look at one of the ECCV paper that we did, what we did is we're going to make sure that everything, when it's transformed here, it will be consistent with clustering property. Clustering property where things similar in this space and need to sit together in this space. And now the tool for you to do that, again, is through this Wasserstein distance.
All right, I'll take this as a short answer to a short question. Thanks very much. Let's thank him once more.
Thank you.